Chapter 2, Exercise 22. Show that if A and B are non-empty sets, then the intersection of A union B is equal to the intersection of A intersect the intersection of B. Right, so I don't think we've seen, at least in the videos I've done, we've seen this symbol right here. It's pretty much like the arbitrary union of sets, only that you're doing it with intersection. That doesn't tell you much. But let's say if you have the union of A, and there's going to be the set of X such that there exists some X in A such that little x is in big X, right? So it's going to be all the elements that are contained within the sets of A that are contained, within some set of A. If X shows up in any member of A, then it's part of the union. So you have something like 1, 2, and then maybe something like 3, 4, and then the set just 1 as an example. Then the union of A is going to be the numbers 1, 2, 3, and 4. And the intersection of A, by contrast, is the set of X such that for all big X in A, little x is in big X. Yeah. So using the same example, 1 shows up. Oh shoot, I made a mistake. Whatever. Using this example, then you have 1 here, which shows up in this set. It shows up in this set, but it doesn't show up in this set. Thus, it can't be in the intersection of A. 2 shows up only in this set, so it can't be in the intersection. 3 shows up in the only shows up here for the same thing. So this is going to be the empty set. If we have a set B that were something like 1, 2, and then 1, 3, and then 1, 4, for instance, then the intersection of B would be equal to the set containing 1, since 1 shows up in all the elements of B. So that's the basic idea of how this operation works. Now with that said, let's get on with the proof. And it's going to be pretty much the exact same thing as all the arbitrary union proofs we've been doing. So let's suppose that little x is in the intersection of A union B. Then for all big X in A union B, little x is in big X, right? What we're trying to show is that little x is in the intersection of A intersect the intersection of B, right? So let's see. So now if there's 3 cases, oops, oh my god, for x. 1 is that x is in A, 2 is that x is in B, and 3 is that x is in A and x is in B, right? So let's do each one. Okay, first case, if x is in A, then x is in A union B. So by assumption, little x is in big X. I don't think that's quite clear. So let's do this. I think this is a better way to phrase it. We want to pick an arbitrary element of intersection A and an arbitrary element of intersection B, and then show that X is in both of them. So let's say, suppose X sub A is in A, right? Then X sub A is in A union B, since A is a subset of A union B. And then by assumption, X, since little x is in the intersection of A union B, then X is going to be in XA, right? So what this tells us is that for any, for all, however you want to say it, X sub A in A, little x is going to be in X sub A. So rewriting this, for all X sub A in A, little x is in A, which is a necessary and sufficient condition for saying that X is in the intersection of A. Right. So that's how you show that X is in the intersection of A. And now I want to show that it's also in the intersection of B. Give me 1 second, add a page. All right. Now consider, X sub B in B. So since B is a subset of A union B, X sub B is in A union B. So by assumption, little x is going to be in X sub B. So for any arbitrary X sub B in B, this is just any element you pick out from the set B, little x is going to be in X sub B. So little x has to be in the intersection of B. We have that little x is in the intersection of A and little x is in the intersection of B. So it follows that x is in the intersection of A, or rather the intersection of the intersection of A and the intersection of B. Okay. Thus, the intersection of A union B is a subset of the intersection of intersect the intersection of B. Cool. Now let's do the other side. And let's suppose little x is in the intersection of A, intersect the intersection of B. Then x is in the intersection of A, and x is in the intersection of B. Right. So how do we show this again? Let's suppose big X is in A union B, and we want to show that this little x is contained in this big X. So then either, or rather than 1, x is in A, or 2, x is in B, or 3, x is in A and x is in B, which, as usual, just degenerate to showing that these two are true. Okay. If x is in A, then little x has to be in x, as x is in the intersection of A. Then if big X is in B, then little x has to be in big X, as little x is in the intersection of B. And if x is in A and and big X is in B, then I keep forgetting to label these. I hope it doesn't distract too much from the flow. Then both 1 and 2 apply. Right. So regardless of choice of x, of big X that is, little x is an x. In other words, for all big X in A union B, let's put this down here. Or no, let's keep it up there. Sorry. Little x is in big X. Thus, x has to be in the intersection of A union B, meaning that the intersection of A intersect the intersection of B has to be a subset of the intersection of A union B. And now, finally, we conclude that the intersection of A union B is equal to the intersection of A intersect the intersection of B. And there you have it. That is how you show that these two sets are in fact the same set. I hope this was helpful. I will see you in the next video. Bye bye.